Hello, I'm Rika Arakawa, a second-year master's student from the University of Tokyo. Today, I will present our work, Hand with Sensing Sphere, Body-Centered Spatial Interactions with a Hand-Worn Spherical Camera. Leveraging spatial context around the body has long been important for realizing natural human-computer interaction. Body-centered spatial interactions are considered to be intuitive, precise, and effortless based on our well-honed sense of self-movement and body position called proprioception. In particular, as hands are one of the most natural input modalities for humans, many studies have explored hand-based body-centered interactions. Previous studies have predominantly focused on sensing and utilizing two types of context for the interactions: hand location and hand posture around the body surface. Interactions making use of the entire body surface have long been a topic of interest for developing body-centered spatial interactions. One of the origins can be found in body mnemonics, where it was emphasized that portable devices would use the entire body space for retrieving information to ease the cognitive load of device usage. Chan and Lee proposed a bootstrapping approach, using accelerometers embedded in smartphones for enhancing access to its functionality through body tapping. Another example is TouchCam, which is a finger-worn device consisting of an IMU, camera, and infrared sensor to estimate coarse touch locations: ear, shoulder, thigh, and hand. On the other hand, there are also many works to sense the context of hand posture. One popular direction is the use of vision sensors. Based on the ability to capture information in a large area, it has become common to use vision sensors in the form of wearable devices to achieve hand-based interactions. Despite many approaches to capturing the two contexts individually, few works have proposed an approach to realizing both hand location recognition and posture recognition simultaneously. Such a sensing module is desirable as it can enhance the hand-based interaction by enabling the users to utilize both kinds of context simultaneously. Moreover, it would offer an opportunity to design and investigate novel body-centered spatial interactions that use location-dependent hand postures as input. In this paper, we propose a novel all-in-one approach to sensing both hand location and hand posture on the body. The primary novelty of a wearable prototype is its use of a spherical camera to capture information sufficient for recognizing both pieces of contextual information simultaneously. Our method takes a data-driven approach with images captured from a spherical camera that is attached to the back of the hand such that it does not interfere with hand movements. We will demonstrate that the proposed approach can detect four contexts of the hand: hand location, hand posture, hand key points, and near hand environment. This is a video showing sample sensor images. The spherical camera creates a unique view according to the hand location and hand posture. We investigate how this achieves an all-in-one approach to sense the context around the body surface. In this work, we focused on sensing the two contexts we have discussed so far: hand location and hand posture. I will explain the model development process for each task. Hand location recognition was performed by learning how body parts look when touched and classifying views during runtime. We used the coarse division of body parts as interaction regions and chose to use 11 body parts in our study, so that many body parts can be employed as candidates for users to choose for the interaction. The division is shown in the figure. We developed a neural network model based on a fine-tuning approach using a ResNet-50 architecture. The images were resized into 224 by 224 pixels. Note that the model is suitable for the real-time use. When learning the inference of the model on the PC with a GPU, it was able to perform hand location recognition with an average frame rate of 12 FPS. Similarly, we developed another model for hand posture recognition. We initially attempted to use existing frameworks for visual hand key points recognition like OpenPose and MediaPipe. However, unfortunately, our tests with these frameworks did not give satisfactory results. This is likely due to the unique view of the hand produced by a 360 degrees camera mounted on the back of the hand. We focused on the postures formed by opening and closing the fingers, resulting in 5 hand postures. Then we applied a heuristic to crop images based on predefined region of interest, which is shown in the right column of this figure. The cropped images are, in turn, used for training a neural network model, similarly to developing the hand location model. Next, I'll explain the procedure for data collection. Participants were asked to wear the prototype and to pose each location or posture. Then they walked around the university campus during different times of day while we recorded the video stream. After we collected the data, we randomly extracted images from the video streams. To make sure the dataset cleaned for training, we manually inspected and removed images where locations and postures were not captured correctly. Consequently, there are a total of 360,000 images used for training, with between 22,000 to 38,000 images for each of the 11 location classes. Similarly, there are 100,000 images with between 18,000 to 26,000 images for each of the 5 posture classes. The overall frame-by-frame accuracy was 85% and 88.9% respectively. From the result, we confirm that the model can successfully identify hand location and posture on the body surface, regardless of the user. So this is a demo for the 2 models. First, leveraging the unique view caused by different hand locations on the body, we can recognize where the hand is touching. Secondly, the hand posture also creates a unique shape around a fixed area in the image. We can utilize this feature to recognize the hand posture formed by each finger movement. The potential of a hand with sensing sphere is not limited to sensing the context of the hand on which the device is mounted. We demonstrate further exploitation of the camera's unique perspective to realize other recognition techniques. Namely, we show approaches to sensing hand key points and near-hand environment. By applying the existing hand tracking models, we can also track the key points of the other hand in specific body postures, such as putting the hands in front or placing the hand onto the other arm. In addition, as the camera is fixed to the hand, the location of the fingertip of the index finger is stable when it is extended. The system can leverage this feature to interact with the environment. So far, we have shown a wide variety of recognition techniques with a hand-worn spherical camera, hand location, hand posture, hand key points, and near-hand environment. Next, we show various interaction scenarios combining these recognition techniques. First, we can use the entire body as an interaction platform. For example, we can trigger apps by touching body parts such as answering phone call. We can further expand this interaction by combining the hand posture recognition. For example, general categories are separated by body part, and hand postures are used to select from the candidates within the category. By leveraging hand key point recognition, we can also achieve an input for continuous value. For example, controlling the music volume by stroking the forearm that affects the size of the hand in the image. The ability to see the environment is another advantage of the prototype. By pointing at an object in the hand, object recognition is possible, as the fingertip and the object are aligned in the view. So far, we have shown that the hand-wound spherical camera can sense a variety of contexts related to hands around the body surface, along with a broad range of use cases. However, some limitations exist in the prototype, which come as a trade-off for using a camera, such as privacy, power consumption, lighting condition, and form factor. First, the privacy of users can be an issue when considering practical applications. We need to adapt design and implementing strategies to mitigate this issue. Another practical limitation of the current prototype is that the camera is wired. Since we will resize the images into lower resolution, we could have used a smaller and lower resolution camera instead of a commercial action camera, which has a high resolution. We need to evaluate if the lower resolution sensor will degrade the performance severely or not. Also, the performance of the proposed system can deteriorate in low light environments. One approach to resolving this issue is to make use of an infrared camera instead of an RGB camera. To investigate how well our recognition approaches might work using an infrared camera, we tried classifying the images after converting them into grayscale images using the same model structure. The overall accuracy was 79.3% for the location recognition and 86.3% for the posture recognition. Although this suggests that using infrared images may be a possible solution to operating in low light conditions, further investigation with an actual infrared camera is required. Future application scenarios should be designed by taking this issue into account. Lastly, attaching the camera onto the back of the hand raises an issue regarding its form factor. As an alternative, we have tried attaching the camera to the wrist, but this resulted in us not being able to capture the movement of the index finger. Still, we believe that hand location recognition and hand posture recognition without the index finger would be possible, supporting the development of a watch-shaped device that incorporates these features. For the detailed discussion regarding this limitation, please refer to the paper. Future work will evaluate the usability of the listed interactions through a user study. In particular, storing information in a hierarchical manner using a location-dependent hand posture is a novel interaction that the proposed system achieves. Secondly, future work will also explore alternative neural network models for use in inferring hand locations and postures. We use ResNet 50 in this work based on its relatively high inference speed and ease of training. In other words, its fast convergence. However, alternatives with similar properties, like mobile nets, do exist, so we need to compare those models. Moreover, the ability to identify the sensor location on the body surface is expected to contribute to more on-body interactions than just hand-based ones. For example, owing to the growing number of wearable devices, there is a demand for allowing tools to be aware of their on-body position. In this context, our approach of utilizing a spherical camera will serve as a module of positioning system on the body. Thank you for listening. We are open to any questions.